For decades, AI development was defined by narrow specialization. Engineers had to build a specific, isolated pipeline for every unique problem. This diagram illustrates that fragmentation. A translation system, a summarizer, and a sentiment classifier existed as three distinct robots, each mapped to one specific output. Because these systems were isolated, they could not share knowledge. A model that understood the grammar of a summary provided no benefit to a model trying to translate a sentence. The shift toward general-purpose AI is shown in this architecture. Instead of siloed pipelines, multiple diverse tasks are now routed through a single central LLM node. This single system handles question answering, text analysis, and code generation simultaneously, without requiring a programmer to write specific rules for any of those tasks. This versatility is an emergent property. The model is not programmed for 50 different jobs. It is optimized for one universal task, predicting the next piece of data in a sequence. To an LLM, text is a series of small units called tokens. Its base action is to identify the specific token that logically follows the sequence it has just processed. The engine driving that prediction is conditional probability. This formula, P of A given B, represents the mathematical likelihood of an event occurring based on a previous event. The model calculates the next token's likelihood by analyzing the exact pattern of all preceding tokens. These calculations are not limited to the word immediately preceding the blank. The model evaluates statistical patterns across the entire input sequence. The capacity for multi-step reasoning is built upon this foundation, the raw statistical probability of each subsequent unit of data. Scaling these probability calculations to millions of words requires a specific neural network architecture, known as the transformer. Transformers abandon sequential left-to-right reading. Instead, they look at all tokens in the input at once to identify which parts of the text are most relevant to each other. Reading everything simultaneously creates a problem. The model loses the natural order of the words. It needs a mathematical way to remember sentence structure. As shown in this schematic, positional encodings are added to input tokens. This assigns numerical sequence data, allowing the internal decoder and self-attention layers to track complex relationships far apart in the text. These relationships are stored in parameters, billions of internal adjustable values distributed across massive arrays of parallel GPUs. The transformer provides the structural capacity to learn, but without a multi-stage training pipeline, it is merely an empty vessel. The first stage is pre-training. An empty model is fed massive text corpora, practicing predicting the next token across billions of iterations, adjusting parameters upon mistakes. The model absorbs grammar and facts, but only knows how to continue sequences. Ask a question, and it might just reply with another question. To make it conversational, we move to instruction fine-tuning, training the model on structured prompt and response pairs. This teaches it to follow a direct command and format its reply appropriately. While pre-training gives the model its knowledge of the world, instruction fine-tuning builds the behavioral interface that allows us to use it. Stage 2 models can converse, but they struggle with subjective queries where there is no single correct answer, like adjusting a letter's tone. Stage 3, preference fine-tuning, uses reinforcement learning to align the model's internal choices with human helpfulness, utility, and safety. A human evaluates two different generated responses. Choosing the preferred one sends a positive signal into the model's logic tree. These choices train a separate reward model to automatically predict human preference. The main LLM continuously updates its internal parameters based on these reward signals, optimizing for the highest possible grade. This stage ensures the model doesn't just output grammatically correct text, but output that is useful for human interaction. Subjective tasks are different from mathematics or formal logic. In these domains, human preference is irrelevant because an objective truth exists. Stage 4, reasoning fine-tuning, is built specifically to sharpen the model's multi-step logical deduction. This stage uses reinforcement learning with verifiable rewards, replacing human feedback with mathematical correctness. The model generates a sequence of logical steps to solve a problem, checking its final answer against a known truth. A correct final answer assigns a reward, reinforcing the entire logical chain. This process allows the model to independently sharpen its internal logic networks, using objective truth as the ultimate training signal. We have to ask what exactly makes these models large compared to the limited AI systems of the past. This diagram shows the limitation of small models. When constrained by less compute and smaller datasets, they can mimic style but struggle to perform abstraction or reasoning. Large refers to the massive expansion of three specific vectors: the number of parameters, the diversity of the training data, and the raw compute used to train it. As illustrated here, when these vectors hit a certain scale, the model begins to perform multi-step reasoning, solving problems it was never explicitly programmed to handle. This reasoning capability is not a hard-coded feature. It is an emergent property that only unlocks when absolute mathematical scale is achieved. Pre-training builds the raw knowledge base, while instruction fine-tuning builds the conversational interface. Preference fine-tuning aligns the model with human utility, and reasoning fine-tuning sharpens its logical deduction. Beneath the conversational interface, the system remains a collection of billions of numerical weights, each one tuned by the specific reinforcement signals of the training process. The appearance of intelligence is ultimately the result of a deterministic probability engine, shaped by strict reinforcement protocols. The role of the AI engineer is to master this four-stage pipeline to turn raw statistical noise into structured reasoning.